Welcome to this lecture in PHAY0031. Today we're going to talk about a special technique called dynamic vapour absorption. And because it won't take long, we're also going to talk about what happens if we put more than one technique together. And we call that hyphenating techniques. So making two different measurements on the sample at the same time. So if you haven't done so already, go and make yourself a cup of tea, get yourself comfortable, and let's make a start. So the learning outcomes from today are to understand the principles of dynamic vapour absorption, or DVS as I've called it on the screen, to give examples of the use of DVS, and that's pharmaceutical examples of DVS, and I've got to tell you there aren't that many, so it shouldn't be too difficult, and also to be able to interpret DVS data. Again, there are very few examples for pharmaceutical applications of how we use DVS, and so interpretation isn't really that difficult. You just got to get your head around what the data are showing, but really it's all about water absorption, so it's not too difficult. Once we've done that, we're going to take a break. In the second part of the lecture, we're then going to look at hyphenated techniques or combined techniques, so two techniques put together. You might have heard of some, so for instance, mass spectrometry is often coupled with TGA, for instance. It's called evolved gas analysis. So we're not looking at that today, but we are going to look at three hyphenated techniques that I think are particularly useful. So one of them is DVS, because that's what the lecture is about, so DVS with NIR. And the reason we're talking about that is because we have one in the school and we developed it many years ago, so we have some examples for that. And then we're going to look at two techniques involving DSC, because if you remember from the DSC lecture, DSC can be quite difficult to interpret because although it measures lots of phase changes, those phase changes appear either as XR or endotherms. So the question is, how do you determine what's going on? And that's not easy if you don't have another technique. So I'm going to give you some examples. That's DSC Raman and DSC X-ray diffraction. So by the end of the lecture, you should understand why we link those techniques together and what you can do in terms of interpreting samples with DSC, either with Raman or with X-ray diffraction. Okay. So we'll start with dynamic vapour absorption. So I should point out right at the start that we nearly always refer to that as DVS. Okay, so if someone says, I'm going to go and do a DVS measurement, that's what they're talking about. They're not talking about doing something devious. It's one of those words in the English language that happens to sound like a three-letter acronym. So DVS is not devious. It's actually very useful. Yeah, remember that. So the other thing I want to say is that in America, DVS is often called GVS, which stands for gravimetric vapour absorption. So if you ever see that written in a paper that's published by an American author, we've done GVS or gravimetric vapour absorption. Just remember it's the same thing. It's just we happen to call it dynamic vapour absorption. One of our instruments, I've got a picture of it coming up in a minute, is by TA Instruments, as a lot of our instruments are, and it's called a surface analyzer, just to make things even more complicated. So it's called a surface analyzer, but really it's still a DVS instrument. Okay, and for me, surface analysis means something different. So surface analysis often means surface energy, which I think we've talked about before with inverse phase gas chromatography, or sometimes it can also mean BET, which is a method of measuring surface area. So personally, I don't like the term surface analyzer, but I just want you to recognise that the instrument, at least in my lab, is called a surface analyzer, so kind of important. What is DVS and what does it do? It's very similar to TGA. So if you remember in TGA, thermogravimetric analysis, your sample is sitting on a balance, and it's the mass of that sample is being measured as a function of temperature. So this is almost the same thing. The sample is still sitting on a balance, but now rather than increasing the temperature, we are increasing the relative humidity or relative vapour pressure of the air surrounding the sample. Now I'm being careful with my words there. Relative humidity is the term that we use when we're increasing the proportion of water in the air surrounding the sample. Relative vapour pressure applies to any other solvent. Now typically in a DVS experiment we don't use really aggressive solvents because it tends to destroy the inside of the instrument. So most of the instruments use water, and so we can use the term RH, and that is fine. But there are limited cases when we might use something like ethanol, for instance, in which case technically we should plot relative vapour pressure. But really it's relative humidity most of the time. So very much like a TGA, and there is actually a diagram of a TGA coming up because it's so similar, your sample is sitting on the end of a really fine microbalance. The entire sensitivity of the technique is dependent upon the balance. So the more sensitive you can make that balance, the better the measurement you're going to make. So the sample sits in the balance and it's surrounded by a chamber, and the air flowing through that chamber is controlled, and we can control it by increasing or decreasing the relative humidity or relative vapor pressure. We usually do that in the software, and the instrument is actually doing something to control how much moisture or how much solvent is in the air. So as I said already, the basic principles of DVS is very similar to TGA. So as a consequence, there is a picture of a TGA instrument on the screen in front of you. Now, I didn't talk to you about TGA, which means I haven't had a chance to talk to you about the design of the balance. But the balance is really critical. And it's a special type of balance called a null adjust balance. Okay? Now, how does that work? I don't hear you ask. And the answer is, I'm going to demonstrate with this coat hook. Okay, so imagine this coat hook is the top of the balance mechanism. On the screen, I hope you can see that in the box at the top there is a diamond shape, and that diamond shape is the top of the balance mechanism. So imagine this is the top of the balance mechanism. Imagine we have a hang down wire coming off one side, and at the bottom of that wire the sample is sitting in a pan in a little crucible. Okay, on the other side of this balance there is a counterweight. So that's the small rectangle shown in the picture. It's kind of important when you set up a DVS experiment that you understand what your sample mass is going to be. So for a pharmaceutical material, we might weigh somewhere between, say, 5 and 20 milligrams of sample. That means that the counterweight also needs to be around 20-30 milligrams so that it effectively balances your sample weight, and the balance isn't doing too much work. Can you imagine that if you had a house brick on one side of the balance mechanism and your sample only weighed 20 or 30 milligrams, then the weight of that balance is going to be heavily skewed towards the reference weight, and that's not helpful. A few years ago I had someone come over from UCL's, I think it was the Bartlett School, and they wanted to make measurements on samples of brick. So they had brick powder particles, but quite heavy chunks. And they said, can we use the DVS to make measurements on those brick samples? And we couldn't do it. And the reason is because the sample weight is designed to accommodate, the reference weight is designed to accommodate samples of about 20 or 30 milligrams. And it just couldn't cope with 1 gram of brick sample because it skews the balance too much. It's very much like when you go up and down in a lift shaft, actually. If you ever watch a modern lift, you'll see that the lift itself has a counterweight on the other side. So as it's moving up and down, it's balancing the weight of the lift, and it's only the weight of the person moving inside which the mechanism is coping with. Right. So the top of the balance looks a bit like a coat hanger, sample on one side, reference weight on the other. At the top of the balance there's a laser. So imagine if I look at it this way, the laser is shining through the top of this coat hanger in this case. So imagine this wasn't a hook, imagine this was like a solid piece. When this is in the null position, so null means at its neutral position, as the laser shines across, it won't reach the other side, and so there's a detector on the other side, it won't see the laser, and so the system knows that the balance is in its null position. Okay. Over here, your sample is sitting on this hang down wire in the pan at the bottom, and you start to increase the humidity of the experiment. So what will happen is water is going to start to absorb onto your sample, and that's going to make your sample heavier. Remember, in TGA, you're heating the sample up, and so when you heat it up, you're either drying the sample or you're decomposing the sample, and if it decomposes to a gaseous product, material is lost. So in a TGA, the sample never goes up in weight, it always goes down in weight because it's losing material. Whereas in DVS it's the opposite. You're humidifying the sample, and really the only thing that's going to happen to your sample is it's going to either adsorb and or absorb water, and so its mass is going to increase. Alright? So your sample is hanging off your hang down wire over here, and it's getting heavier as the relative humidity is increasing. So heavier means there's more weight on this side of your balance, and so that will have the effect of pulling this null position down, because this side is getting heavier. So the heavier this gets, the more this coat hanger, in this case, tips out of balance. The laser is shining through the top here, and it's being blocked by the top of the balance mechanism. As this moves, the laser is able to reach the detector, and so the system knows that the balance is no longer in its null position, because it can now see the laser. So the way this works is, this balance mechanism is connected to an electromagnet. An electromagnet means the more current you pass through it, the more the motor will effectively turn. Think of it like a very small electric motor, but not one that's designed to turn really fast as an actual motor. It's kind of the same mechanism, it's just it's got a small amount of current passing through it, and that will have the effect of rotating it just a little bit. So what will happen is, the system is programmed to keep this balance mechanism in the null position. Null position meaning, as the laser goes through the top, it's not being detected by the detector. As your sample increases in mass, as it becomes more wet, it will pull this balance mechanism around, and so the system responds by putting some current through this motor to drive this back to the null position. It drives it back so that the laser doesn't impact the detector, so that's when it knows it's at the null position. And in simple terms, the amount of current it's had to put through this motor to get this back to the null position is proportional to the mass of the sample. Obviously, the more mass on your sample, the more this is pulled out of position, the more current is required to bring it back to its null position. So the reason the balance is so sensitive is because you're really measuring a voltage, which is very easy to measure, down to very, very small changes in voltage, and the voltage is directly proportional to the mass change. So you can measure some really, really small mass changes in your material. There's another benefit of using this type of balance, in addition to the absolutely amazing sensitivity, and that is that if you look at the picture, you can see that where the sample is sitting on the hang-down wire, that sample is, well, in this case it's a picture of a TGA, so it's amongst a furnace, but in a DVS it would be a chamber through which we're passing the gas. So it doesn't really matter whether you're heating the sample or you're flowing air over that sample. It's kind of important that the sample remains in the same place. So imagine that you're heating that sample from heaters on the side. There's going to be convection carrying that current across, and if you move that sample up or down, the amount of heat it's experienced is going to change. So you kind of want it in the same position every time. The same is true if you're flowing a gas through that sample and you're trying to humidify the sample. You kind of want the sample to be in the same position relative to the gas coming in and out. And as it starts to move, it will either absorb water faster or slower depending on where it is relative to the gas stream. So the beautiful thing about this balance mechanism is that as the sample changes mass, its position in the instrument never changes, because the instrument is always moving back to the null position. So the balance is in the null position, but the sample is always in the same position as well. It's a really clever piece of design. It's the reason why whenever you go and look at a DVS instrument, there'll always be some part of the mechanism on the top, and that mechanism genuinely is a big diamond which is rotating like that. On the screen are two pictures of the instruments that we have in our own laboratory. So that should help you find them should you ever be on the third floor looking for them. Although I've got to tell you, the one on the left, so the blue one, that's the TA Instruments instrument. Every instrument that TA makes is blue. And so if you walk into my laboratory, they all look like that, and it's still difficult to find the DVS. But nonetheless, that's the one that we have. The large grey box on the top is housing the balance mechanism, as I just said. And on the right-hand side, there's a sort of circular mechanism. That is actually an auto sampler. Okay. When we bought the instrument, we specified it with an auto sampler for a good reason, and that reason is the sample sits on a really fine hang-down wire, really thin hang-down wire. And if we allow students to try and load the sample directly onto that hang-down wire, some of you are really quite good and you won't bend the wire, but some of you are a little bit rough with the instrument, and it's really easy to bend that hang-down wire. And as soon as that wire is bent, then we have to change it, which is quite a job. So the auto sampler uses a robot to take the sample from the carousel and it puts it onto the hang down wire for you. So the auto sampler is not there to allow you to run hundreds of samples overnight. It is there to make sure that the hang down wire doesn't get bent when the sample is loaded. The instrument on the right is by a different company. It's called Surface Measurement Systems, or SMS, and we also have two of those systems, or I think only one of them is currently set up. It's basically the same as the TA Instruments system. The only difference is it doesn't have an auto sampler, so you've got to manually load the sample onto the hang down wire. And I think if you're following what I just said, you know what the risk of that is. So that one can often be out of action because the hang down wire is bent. But the reason it's on here is because the SMS system can also flow ethanol, so that's kind of handy. We can look at relative vapor pressure then. And also it's the one that's got the NIR probe linked to it. So sometimes you may want to make measurements both mass of the sample and NIR, and that's the system to go with. The TA Instruments one is just measuring mass as a function of humidity. So let's say you go into the laboratory and you want to set up a DVS experiment. You're going to load your sample onto the hang down wire, or the instrument's going to do it for you. That is fine. Then you've got to program the instrument to do something. And the only thing that the instrument can do is increase the relative humidity of the gas surrounding the sample. And it can do that in one of two ways. It can either increase it linearly according to some sort of ramp. So think with TGA and DSC, you have a constant temperature ramp. So let's, for argument's sake, say 10 degrees a minute. It's the same in the DVS. You can set a constant ramp of, say, 5% relative humidity per minute. Something like that, it doesn't matter. So you can have a linear increase in relative humidity, or more commonly, you can go with steps. So in red on the slide in front of you, that's showing you a stepwise change in relative humidity. So typically you might do that in 5% or 10% steps in humidity. In my experience, using steps is better than using a ramp. And the reason is because, unlike changing temperature, changing humidity can cause the sample to change, but it takes quite a time for that to happen. So you've got water coming into the atmosphere around the sample. That water then has to condense onto the surface of your sample. Maybe the water actually gets inside your sample, but that all takes time. And if you've got a constant ramp going on, how your sample is changing is kind of lagging behind, and it's kind of difficult to work out exactly what your sample is doing at any one particular relative humidity. And if you go in steps, the way we set it up is you increase the relative humidity, let's say to 5%, and then it holds 5%, and it allows the sample to come into equilibrium. Once it's reached equilibrium, it then changes humidity and so on and so forth. It's a kind of a better way of doing the experiment because you can actually see what's happening to your sample at a specific RH. And so that's the way that I would recommend you set it up if you're going to do that. Now there's another way of setting up the experiment if you've got steps, and that is that you can either set the length of each step to be a constant time point. So for argument's sake, let's say 20 minutes. So you change the relative humidity by 5%, hold for 20 minutes. Change by 5%, hold for 20 minutes. So each step is exactly the same length. Or you can say to the instrument, I want you to measure the rate of change in mass. So let's say the relative humidity goes up and your sample starts to absorb water. The rate of change of mass of your sample is going to be changing. You can set it so that the sample comes into equilibrium before the next change in relative humidity. Now there are pros and cons to both of those approaches. Okay, if you do the former, so you have specific time periods at each step, one thing, you know absolutely how long your experiment is going to last. You know the number of steps and the time for each step, so you know when to come back and set up the next experiment. The downside is that you don't know that your sample is going to reach a position of equilibrium within that time period. So one thing you can do is you could set a long time period when you don't know your sample. So let's say 30 minutes or 40 minutes per RH step. And when you come back, you actually look at your sample and you go, did it reach a position of equilibrium or not? If it did, let's say it got to equilibrium after 10 minutes. Then when you set the sample up again, just set the step to 10 minutes because you know that will be enough for your particular sample. The risk, I suppose, with that measurement is you waste time because you're just spending a long time with the sample doing nothing. Whereas if the system is programmed to move on, once it reaches equilibrium, it will automatically move on. So you might say to me, well, wouldn't it be better then always to use the auto program to decide when the system's got to equilibrium and move forward? And I would say kind of no, because we run very busy laboratories and we're in the centre of London, and so it's a very fine micro balance. Someone opening the door to the laboratory or someone casually putting their hand on the table will create noise in the experiment. And if the system is looking for a particular value of rate of change of mass with time before it moves on, quite often, especially during the day, less so if it runs overnight, but during the day, it will never get to that value because there's always someone creating a bit of vibration and it's making the instrument think it's not safe to move on. And so we've had many instances where people have used that type of method and they've come back a day later and it's still on the same relative humidity because it never got flat enough. So in my personal opinion, I would set it up with a defined step length at each humidity, come back and see what it looks like. And if you need to make a particular step longer, go back and do that. But it's a lot safer than letting the system move forward and never actually getting through the RHs that you're programming. Now, let's have a little drink. Very good. On the screen in front of you are some typical DVS data that you might record for a pharmaceutical powder. Okay, there's two lines, one in blue and one in red. Now, the reason I've got two sets of data on the same axes is because there really are very few things that can happen in a DVS experiment if you're running a pharmaceutical sample. Okay, that makes your life a lot easier when it comes to interpreting the data because there's very little that can actually happen, right? So the reason I've got two examples on here is because they are the two most common types of sample that you might study. So I'm going to tell you what the two samples are, and then I'm going to let you just have a moment to think about which one is which in this DVS trace. Okay, so the two samples are an amorphous powder and a crystalline powder of the same material. They're both lactose. So crystalline lactose and amorphous lactose. So while I finish my coffee, I just want you to look at those data and think to yourself, which one is which? Is the red one crystalline or is the red one amorphous? So just have a little think about which one is which. And if you've done that, think to yourself, why do they look different? Why do the two look different? So let me finish my coffee and then we'll have a discussion about it. Okay, that was actually quite a bit of coffee, wasn't it? So, but it's still not a long time to think about it. So if you want to, just pause the video and have a think. When you're ready, press play, okay? And then I'll tell you. Okay, right. Crystalline is, wait for it, the blue one. Okay, if you said crystalline is blue, very good, get a gold star, which means that amorphous is the red one. Why are they different and what could you have done to guess that? Okay. If it was me, I would say that crystalline materials are quite stable and therefore there's very little that can happen to a crystalline material, and if you look at the data on the screen, there's very little happening in the blue set of data. So right from the get-go, it would be fair to say blue is probably crystalline because not much is happening, and I would agree with that. Okay, the only thing that a crystalline material can do is adsorb water onto its surface. Okay. On the other hand, amorphous materials are a bit more tricky and they can do more things. So firstly, not only can they adsorb water onto the surface, they can also absorb water into their core, because remember, amorphous means randomly structured, so there's space between molecules. So in this instance, the gradient on the red line is higher than the gradient on the blue line, and the reason is because that sample is both adsorbing and absorbing water. And that's an indicator right there that it's amorphous, because the rate of increase of mass is greater. There's one other thing that you might notice about the red, which is that right at the start of this lecture I said, in a TGA, the sample mass only ever goes down, and in a DVS, the sample mass only ever goes up. You might reasonably say to me at this point, hang on a minute, Simon, the data in the red have clearly gone down, and I would agree with you. And it's an interesting case. So, if in a DVS experiment you see a mass increase and then a mass loss. That's really characteristic, and it's characteristic of an amorphous material. I can't think of any other pharmaceutical material that shows both an increase and then a decrease in mass. So if you want one take-home message from the first part of this lecture, it is that if you're looking at a DVS experiment and you see a mass increase followed by a mass decrease, that is absolutely characteristic of an amorphous material. So if you're making some sort of measurement and the question is my material amorphous or crystalline, then a mass loss like this is absolutely a clear indicator that the material is amorphous. Why? What is it that's happening to the sample to make it lose mass? The answer is it is adsorbing and absorbing quite a lot of water into its structure. Water acts as a plasticizer, and a plasticizer means you're increasing the chance of the material crystallizing. So what is happening in the DVS trace here is that to start with, at low relative humidities, so under about 55% on the graph, the material is add and absorbing water. But it reaches a critical point around about 55% relative humidity where the amount of water that is add and absorbed is so high it forces the material to crystallize. As the material crystallizes, remember, the molecules which were randomly structured suddenly become structured and the space between them becomes a lot less. So any water which has been absorbed by that material, now there's no room for that water anymore because the drug molecules have become much more tightly packed. And so the only option that the material has is to expel that water into the gas stream and it's carried away to waste. But because that water has been lost by the sample, there is a decrease in mass. So we see an increase as the material is add and absorbing water, and then we see a decrease as the material crystallizes and it expels that water. It's a really characteristic thing for DVS, probably the most important thing that you need to remember from this lecture. Crystalline materials generally just increase and amorphous materials increase and decrease as they crystallize. You might say to me, why is there a really rapid increase in mass at the end for both samples, both the crystalline and amorphous? And I would say to you that's because when you get to very high humidities, typically 90% and above, you start to get condensation of water onto the sample, so droplets of water onto the sample. It's not really reflective of surface absorption anymore, it's actually condensation. So we don't normally run the DVS to that higher percentage because you can get spurious results. Right, on the screen is an example of a real material that one of my students, MSc student of course, made many years ago. It's a freeze-dried sample of terbutaline sulfate. So freeze-dried means it's amorphous. So on the screen you can see dm by dt, so rate of change of mass, on the left-hand axis, and the relative humidity that's being programmed on the right-hand side. Relative humidity is shown in dots. So you can see we went up in steps, and then the solid line is how the material is responding. I hope you can see that we have an increase and then a decrease to around about 75% humidity. And we would call that a critical humidity because that's the humidity at which it's caused the material to crystallize. Another example, same student, now it's salbutamol sulfate, same set of data. Now you can see that the critical humidity is a little bit lower, it's around about 65%. So DVS is a really useful technique for determining what the critical RH is of a particular material. Critical RH meaning it's that RH which below you could probably store the material and it will be reasonably stable, but above you're going to crystallize that material and you probably don't want to do that. Right, so with that we're going to take a break. When we come back we're going to look at how we link techniques together to form hyphenated techniques. So get a cup of tea, have a break, and I'll see you in a minute.